All right, so we are continuing our discussion of section 7.2. We're talking about series. And we want to know if a series is the sum, an infinite sum of terms from a sequence. And we want to know if when we add up those terms of the sequence, does the series converge or diverge? So last class, we looked at, for instance, geometric series. We looked at harmonic series. And we're going to continue looking at series today. You're going to learn about a few other kinds of series. Let me give you a moment to copy this example down, and then we'll go over the solution. Okay, so we look at this series, and we want to determine if this series here converges or diverges. So naturally, what matters to tell you if a series converges or diverges is not how the terms at the start of the series behave, but how do the terms behave as we move further into the series? In other words, as n gets larger and larger. So one thing that we can think about here is if we look at this series, okay, if we look at this series, and let me see here, let me get my little pen out. Okay, hold on, I just got to change the font level. Okay, if we look at this series, when n is large, does the 1 in the numerator and the 1 in the denominator affect the value of the terms of the series when n is large? It does not. It does not. That's right, Nathaniel. So essentially, as n is large, the terms of the series almost equal n divided by 5n. And n divided by 5n is a fifth. So this series, the terms of the series, as we move out into the series for large n, the terms of the series are approaching a fifth. So it's like we're adding up eventually a fifth plus a fifth plus a fifth plus a fifth plus a fifth and so forth. So would this series, do you think, converge or diverge based on that? That's right. That's right, Nathaniel. It would have to diverge. So what I'm trying to do is I'm giving you an intuitive feel for trying to give you an intuitive feel for these series to help you determine, just to help you feel comfortable when a series converges or diverges. Now, what I'm really saying here is I'm really utilizing what's called the test for divergence. So if we look here at the solution, the test for divergence says, look at the terms of the series when n is large. Well, when n is large, okay, the terms of the series approach 1/5. Now, I can be a little more formal on this, okay? I can be a little more formal regarding this limit. I mean, we have the limit as n approaches infinity of n minus 1 over 5n minus 1. And what I can do is multiply the numerator and the denominator by 1 over n. Okay, and when we do that, we're going to get the limit as n approaches infinity of 1 minus 1 over n divided by, hold on, I need a little more space here. Okay, divided by 5 minus 1 over n. Okay, so we just distribute the 1 over n's, you know, to the terms. And this is what we'll get. Now, clearly, as n gets large, right, as n gets large, these terms here go to 0, the 1 over n terms. They approach 0. And so when you take the limit, you'll get a fifth. I mean, that's being very formal on computing the limit. But intuitively, you know that the limit of the terms of the series approach a fifth or equal a fifth. And so the terms of the series approach a fifth. And since the fifth is not equal to 0, the series diverges by the test for divergence. In order for a series to converge, what do the terms of the series have to approach? What value do the terms of the series have to approach for the series to have it, for the infinite series to have a chance of converging? That's right, Tosh. The terms of the series have to approach 0. Now, that doesn't mean, though, that a series whose terms are approaching 0 converges. Because remember, we talked about, for instance, the harmonic series. The harmonic series. Okay, the harmonic series Okay, you have 1 plus a half plus a third and so forth. So those terms of the series are getting smaller and smaller, but this series diverges. Okay. But certainly if the terms of the series are not approaching 0, the series is definitely going to diverge. So what I did here was I wrote this series. I wanted to put a little bit of detail. I wrote out the first 4 terms of the series here. First 4 terms of the series. And then what's this term here? 4,999 over 2,499. What term of the series is that? That's a sub what? A sub. That's right, Ange. A sub 5,000. Okay, hold on. I like things to be neat. And then here is the 5,000 first term. Which is 5,000 over 25,004. Why this keeps popping up? You see this pop up that I'm seeing? I don't know. Hopefully, I don't know if it's showing. I don't know. Sometimes my stylus, I touch it and stuff pops up. I think there's a setting I can do so that doesn't happen. I'll have to figure that out. But at any rate, you know, here are the 5,000th term and 5,000 first term, and you can see how close those are to a fifth, those terms. So the series will equal infinity because eventually you're adding terms that are basically very close to being equal to a fifth. So if you add a fifth infinitely many times, you're going to get infinity. Okay, so that's the test for divergence. Are there any questions on that? Okay. Well, let's then let's proceed on to another example, if we're good on this one. You know, I always like using intuition to help me. I mean, you know, ultimately, of course, math is, you have to use the math, but intuition is worth a lot when you're dealing with sequences and series. All right, let's go to another example. Let me give you a moment to copy this example down. Okay, so this is an interesting series here. So let me ask you, if you have a series like this, a series where you have AN plus BN, what do you think we can write that series as? We have the series of a sum. The series of a sum would be the sum of the series. That's right, Taj. So see, we can separate. Like you see here. See that? I mean, it makes sense, right? It makes sense that we ought to be able to do that. And so I'd like to apply that for our situation. Okay, are there any questions on that? All right. Well, let's go to the solution here. All right, so first thing I do is I separate, I write, I have a series of a sum, that's the sum of these two series. So that's just applying the rule. That's applying this rule here. Okay, and then we know that constants like the 4 here can be brought out in front of the summation. And the 3 on the second summation can be brought out in front of that summation. So that gets us down to here. Take a look at it. Okay, so hopefully everything's good so far. Now what we have are two series that we have to deal with. Let's deal with this series first. This series, what I'm going to do, I mean, you know, the 1 over e to the n in that series can be thought of as 1 to the nth power over e to the nth power. But then I can write the series as a series n equals 1 to infinity of 1 over e to the nth power. And that is just a geometric series, class. That's a geometric series with common ratio equal to 1 over e. That's a geometric series with a common ratio of 1 over e. So we learned that okay, in section, hold on, let me get the, one moment. In section 8.2, we learned about geometric series, and we learned that under certain conditions, a geometric series will converge. And so formula 4 in the book, okay, this is the formula. Any geometric, so, you know, geometric series, any geometric series can be written this way. And it will have a sum of a divided by 1 minus r, so long as the absolute value of the common ratio is less than 1. Well, this common ratio that we have of, hold on here, of 1 over e, that common ratio is less than 1. And so I can write the formula, I can write the sum. That series converges to 1 over e divided by 1 over 1 minus c. I can make things a little prettier by multiplying by top and bottom by e. And if I do that, I'll get 1 over e minus 1. Okay, so that, the first series was a geometric series that converged, and we know its sum. Are there any questions on that? All right, well, let's look now then at this second series. Wow. This second series is certainly an interesting series. It's not harmonic, it's not geometric, it's like a new kind of series that you've not seen before. And we call this kind of series a telescoping series. Now, why is that? Why is that? Well, let's go ahead, if we're good here, let's go to the next page. And of course, we want to know, I mean, does this series converge? Does it converge? We know this series, the first series, converges. We know that. What about the second series? So these kind of series come up. They come up in math, these telescoping series. And let me show you how we deal with it. So first thing I'm going to do is I'm just going to write out some terms of the series. So the first term is 1 divided by the denominator 1 times 2. Second term of the series is 1 divided by the denominator 2 times 3. Third term of the series is 1 divided by the denominator 3 times 4, and so forth. Are the terms of the series getting smaller? Are they approaching 0? The terms of this telescoping series? They are. Indeed, they are, Ange. So now that doesn't mean this series converges based on that alone, the fact that the terms are approaching 0. What really depends is how quickly they approach 0, essentially. So, but the way we're going to find, I can tell you this telescoping series is going to converge. And what we're going to do is, we don't have a formula for the sum. So let's see here. We're going to let S sub n be the nth partial sum. Okay, the nth partial sum, or which means the sum of the first n terms of the series. And you learned yesterday, maybe I'll put this in blue, that the limit of the nth partial sums as n goes to infinity equals s. And s is the actual sum of your infinite series. That's what it is. That goes with definition 2 in the textbook. So we're going to define the nth partial sum. Well, not the nth partial sum is going to be the sum of the first n terms of the series. So I starts at 1 and ends at n. Okay, that's the first n terms of the series. So like for instance, if we had s sub 3, s sub 3 would be the partial sum I equals 1 to 3 of 1 over I times I plus 1. That's going to equal 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. It's the third partial sum. It's the sum of the first 3 terms of the series. Okay, so that's what we mean by nth partial sum. But the way the nth partial sum is, the way the term in here is, this is not a convenient form for the term. So, oh man, what are we doing here? I divided by the denominator I times I plus 1 will equal A over I plus B over I plus 1. What kind of expansion is that called? Do you remember? Almost right, Ange. Almost right. Partial fractions. That's right, Taj. This is a partial fraction expansion here. Okay, this is a partial fraction expansion. And since I have the linear terms I and I plus 1 in the denominator, this is the expansion. And of course, what we need to do is solve for A and B. We need to solve for A and B. So what we're going to do, hang on. Okay, what we're going to do here is multiplied by the least common denominator, I times I plus 1. Okay, and when we do that, you've done partial fraction expansions before. You reduce the rational equation to one of these equations, and then you group the like terms. And here, since 1 on the left is equal to 1 plus 0 times I, well, you have to equate the coefficients. The left side of the equation equals the right side. So that means 0 has to equal A plus B, and 1 has to equal A. So therefore, A plus B equals 0, A equals 1, and therefore B is negative 1. Let me give you a moment to copy that. All right, if there are no questions, I'll go ahead and move to the next page. So what we're doing is this nth partial sum, I'm rewriting it. I'm rewriting it so I can find out what the limit of I want to rewrite that nth partial sum in a different way so I can find the limit of the nth partial sum as n goes to infinity. And then if I get a finite limit, that tells me that that second series converges to that limit. So, okay, A equals 1, B equals negative 1. Okay, so let's see here. Okay, here's A. A equals 1. And, really what you have here, right, is then plus a negative 1, right? And so B is the negative 1. Now look what I'm going to do here. Look what I'm going to do. Now over here, I'm going to write out some terms of the nth partial sum. Okay, so that's what I've done. I've taken this nth partial sum here, and I've expanded it out. So, and then I say, okay, well, all of this, like this entire sum here equals 1 over 1, 1 minus 1 over n plus 1. Now, how are we able to basically say that? Well, let me see. Maybe I can give you a few examples. I'm just going to need I'm going to need a little space over here. So one moment. Okay. So all right. So like let's say that you wanted to find, just as an example, let's say, I'm trying to convince you why that formula is correct. All right, hang on. I don't know what I touched here. I don't want to do anything with that. Hold on. What did I touch? I don't know what this is. All right, hold on, class. I'm in some funny thing here. Okay. So like S sub 3, based on you know what we have here, S sub 3 would be 1 minus a half plus a half minus a third plus a third minus a fourth. Now, what terms cancel there? What terms are going to cancel out? For that third partial sum. Okay, that's right, Ange. The halves go out and the thirds go out. And so you're left with 1 minus 1 over 4. So you see which is 1 minus 1 over 3 plus 1. See, the third partial sum is S sub 3, and 4 is 3 plus 1. So what I'm trying to do is I'm trying to justify the n plus 1, down here, why this has to be n plus 1. If we were to do like S sub 4, let's do another one, S sub 4. S sub 4 is 1 minus a half plus a half minus a third plus a third minus a fourth plus a fourth minus a fifth. I mean, are we okay with this? My writing these terms out. I want to make sure that you're comfortable with what I'm writing here. You know, these terms. And is good. Are there any questions at all? Okay, Javier's good. I mean, you know, in the expansion, good. Taj is good. I mean, in the expansion, you know, this is when I is 1. This term is when I is 2. This term here is when I is 3. This term here is when I is n. Okay. All right. So, okay. Well, let's see what this fourth partial sum equals. So the fourth partial sum, well, let's see, do some terms cancel here? The halves go out. Anything else? Do any other terms cancel? Any other fractions? Good, the 1/3 goes out. That's right, Jan, that's right, Ange, okay. And Ange says the 1/4 also, yeah. So sure, and I can use, you know, some different red highlighters here to kind of. So what are you left with? You're left then with the fourth partial sum as 1 minus 1/5, but that equals 1 minus 1 over, well, now let's see, here we have sub 4 there. So 1 over 5, but 5, right, is 4 plus 1. So you see the pattern came up again. So we can deduce that the nth partial sum is equal to 1 minus 1 over n plus 1. And now that we have a formula for the nth partial sum, we can take the limit. We can take the limit of this nth partial sum. And clearly, the limit as n goes, so the limit of the nth partial sum is as n goes to infinity, is the limit of 1 over 1, 1 minus 1 over n plus 1 as n goes to infinity. The 1 over n plus 1, as n gets large, this term is going to go to 0. And so you're going to be left with 1. And so the nth partial sum equals 1. Okay. So what this means then, is that, well, then our summation here equals 1. That's what our sum is. The infinite series equals 1. And therefore the series converges. See how that works? So we would have not been able to find that without writing the sum as a telescoping sum. Now you can't do that for all series, but for certain series, they are telescoping series. Are there any questions? All right, well, let's finish this problem off then. Let's finish this problem off. So now we have here, right, we have, we know that that second series equals 1. And let's remind ourselves that we wrote this series here this way. And then we factored out the 4 from the first series. And factored a 3 out from the second series. And that then gets us, but we've established that the first series, the sum is 1 over e minus 1. And the second series, the sum is 1. So this then gets us here. And this would be fine in WebAssign. I mean, that's the answer. The series this series converges. Series converges. And you can do some math to get the series in a nicer form. You don't have to, but if you wanted to get the series with just like a denominator e minus 1, that's what it would look like. Okay, are there any questions on that problem? How many think that's kind of a cool problem? Okay, Ange does. Thank you, Ange. I was hoping maybe I'd get a couple people to, all right, Taj, thank you. Thank you, Nathaniel. I mean, this is so important in math, these series. I can't tell you how important they are. They come up again and again and again. Uh, and But on that note, I'd like to do one more problem with you before we take our little break. So let me find it here. One moment. All right, if we're good on that, let me find this problem. Hold on, everybody. There it is. Okay, let me give you a moment to copy this example down. Okay, so here, let's see here. Let's see what we have. So we could write this. Hold on, let me get the 3-point. We could write this like this, right? We could write this series, and this is called we call this a power series because we have a variable. We have a variable x that's involved in our series, so we call this a power series. What does this power series remind you of? This power series, does it resemble the form of it, any of the series that you've seen so far? That's right, Ange. A geometric series. That's right. So this power series has the form of a geometric series, and we're going to make use of that. So let's go to the next page and write out some terms of this series. Okay, so what we do here in our solution is I'm writing out some terms of the series up here, just so it gives you. How many find it helpful for these series to write some terms out, maybe the first 3 or 4 terms of the series, just to give them a little intuitive feel for the terms of the series? Is that helpful for anybody? Okay, Taj likes it. Wonderful, wonderful, excellent. And Javier, excellent. All right, so this power series, it's a geometric series with a common ratio r equals x over 3. Now, how am I getting that? How am I getting that? Well, okay, so if I were to take well, first of all, you can kind of guess it from the way we wrote the series. But, you know, if you take the second term divided by the first term, second term is x squared over 9. And we're dividing that by x over 3. So that this gives us x squared over 9 times 3 over x. Hey, there's x over 3, common ratio. And if we were to take, you know, so there's first term, second term, third term, fourth term, and so forth. If we were to take the third term and divide it by the second term, we would also get x over 3. So there's a common ratio of x over 3. But let's remember, a geometric series only converges when the absolute value of the common ratio is less than 1. So you see, with this power series, we have to establish for what values of the variable the series converges. Okay, what values of the variable would the series converge? So I want then that the absolute value of my common ratio here, the absolute value of x over 3 is less than 1. But this then means that x over 3 is less than 1 and greater than negative 1. Certainly then, what we can do is we can multiply by 3 through the inequality. And since 3 is a positive number, the inequality signs don't change. And so this gives us that x is between negative 3 and 3. So this tells us what is called our interval of convergence. We have an interval of convergence. Those are the x values for which the series converges. Okay, so like for example, if you had x equals 2, well, then the power series would become this power series. Now, that would be a convergent power series because x equals 2 falls within the interval of convergence. Now, what's the general formula for the power series? Well, again, remember the sum of a geometric series whose absolute value of the common ratio is less than 1 is a divided by 1 minus a divided by 1 minus r. Common ratio is x over 3, and the first term is x over 3. You can see that up here. I mean, here's your first term. Right? There it is, x over 3. And the common ratio is x over 3. So a divided by 1 minus r would be x over 3 divided by 1 minus x over 3. And that can be simplified to x divided by 3 minus x. That's sum. So now you have a summation formula for your power series. Okay, and so, here's the general formula. Here it is. And so if x, like for instance, were equal to 2, the power series, or the series now, because now we're putting in a value of 2 for x, the series would equal 2 over 3 minus 2, which is 2 over 1, which is 2. See? So that would be the sum. If we had for instance x equals -1, okay, if we were to do x equals -1, well, the series -1 over n to the 3 over n, okay, would equal, well, x is -1 over 3 minus 3 minus -1. That's going to give you -1/4. See that? So see, you got a formula that you can use for different values of x. It's really quite beautiful, isn't it? And this is an important concept that you're going to be seeing likely next week. We'll be getting into this kind of material either next week or the week after. Probably next week, actually. But are there any questions on that? Give me a thumbs up if you're feeling reasonably good with what you're learning here. I'm just curious. All right, Nathaniel is, Taj, Nathaniel, Kiddis, Jan, wonderful. Okay, hold on, my chat thing, Ange and David. All right, great, great. All right, well, if there are there any questions before I stop the recording? All right, I'll stop the recording.